Hello, my name is Michelle Tran, and I plan on specializing in semiconductors and optoelectronics. Thus, today I will be talking about organic flexible electronic devices, which for the most part have an organic semiconductor as their main power source. Hello. Okay, here's a list of the topics I'll be discussing in this presentation. Number one, overview of flexible organic devices. Number two, organic semiconductor material. Three, organic versus inorganic conductive polymers. The next three, four, five, and six are going to be flexible organic devices applications currently being researched. So first, OLEDs, OPDs, OX, and then we're going to finish off with OFEDs. So first, an overview of flexible electronic devices. The development of flexible organic electronic devices, also known as FEDs, is gaining momentum around the world as FEDs will drastically alter many aspects of daily life. They have emerged as a fascinating area of research and technology in the last 2 decades, and they're expected to replace traditional inorganic semiconductors in a wide range of applications. Furthermore, the development and encapsulation of organic electronic devices onto flexible polymeric substrates through large-scale and low-cost roll-to-roll manufacturing processes will enable their market implementation in a wide range of areas, including displays, lighting, both photovoltaics, radio frequency identification circuitry, and chemical sensors, as well as a whole new generation of modern exotic applications. So 2, organic semiconductor material. An organic semiconductor material, or OSM, is a carbon-based material with interesting optical and electronic properties that can be used in a variety of applications. One significant advantage of these organic materials is that their molecular properties can be tuned and adapted to suit the intended application through chemical design. 3, organic versus inorganic conductive polymer. Organic conductive polymers have a much lower conductivity than their inorganic counterparts. However, these materials have its advantages. Because of their high processability, meaning the ability to deposit them on surfaces such as screens through printing methods, and specific mechanical properties, for example, their flexibility, new materials are constantly being developed and applied. So onto the first application of organic flexible electronic devices in the biomedicine sector, OLEDs and OPDs. First of all, OLEDs, or organic light-emitting diode, technology has introduced the general public to the use of organic semiconductors. OLEDs are optoelectronic devices that are able to emit light when an electronic current passes through them. This allows OLED screens to emit light by itself. This means that OLED screens require less layers, less steps to fabricate, and raw materials needed to be manufactured. Not only will it be cheaper to manufacture because of this, less layers means that OLED displays are able to be thinner and lighter, and most importantly, flexible as a result of its compactness. Its ability to flex leads to a whole plethora of future applications. Currently, Samsung has already implemented the use of flexible OLED screens in its Galaxy Z Fold series of phones. Furthermore, the use of flexible OLEDs can be applied to flexible and on-skin wearable sensors for continuous health monitoring, such as with wearable pulse oximeters. In the past, there have been studies that looked into OLEDs integrations into rigid substrates and OPDs, or organic photodetectors, on separate surfaces separately. These organic photodetectors, also called photosensors, are sensors of light or other electromagnetic radiation. These have cost-effective manufacturing techniques using solution processes and tunable spectral range response, which makes them particularly promising as sensors on flexible substrates. This is very similar to that of OLEDs. As such, T-top studies of OLED OPD matrix for sensing on single flexible substrate postulated that combining these two types of technologies together would maximize its effectiveness and cost-saving manufacturing processes, making it a promising alternative to conventional semiconductors in the field of flexible multiplex sensor electronics. Since these two are similar in fabrication, the team sought to test that if OLEDs and OPDs would be able to function simultaneously, resulting in both sensing abilities, OPD's greatest advantage, and clear displays, OLED's greatest advantage. The team found that these units can be laminated into a microfluidic system for liquid sensing applications. To create the OLED OPD matrix on a single flexible plastic substrate, a 6x6 matrix of alternating blue OLEDs and red OPDs were studied, meaning 18 of each were used. You can see this on the screen now. And now. So, ray tracing simulations were conducted to determine the efficiency for fluorescent sensing. Results from the simulation demonstrates that the close distancing of the OLEDs and OPDs to each other leads to any stray light to be effectively suppressed, meaning that both sensors are able to work simultaneously while still having a clear display. It was then placed onto PET, and as such, the individual devices were measured to be 1 millimeter by 1 millimeter, with both the OLEDs and OPDs having been shown to work. Though Titov's and the team's study was based on the concept of pulse oximeter, this is a big step in the right direction for the future of remote patient monitoring in the healthcare sector and the use of organic flexible bioelectronics in biomedicine. Now onto another application of organic flexible electron devices in the biomedicine sector, OX. Because of its great promise in personalized health monitoring and point-of-care diagnosis, flexible bioelectronics, which offers soft, functionalized interfaces to couple biology and electronics, have gained increasing interest. Flexible bioelectronics refer to a class of electronic devices that are built onto stretchable substrates, usually plastic, in order to give it its flexibility capabilities used in the healthcare sector, as it uses multifunctional sensors to obtain various data from the human body. Because of their flexibility, biocompatibility, high transductance, low working voltage, design diversity, and ease of manufacture, organic electrochemical transistors, or OX, have been widely implemented in flexible bioelectronics. And here is a zoomed-in version of that image. The most common semiconductor material used as the channels in OX devices have traditionally been P-type and to a lesser extent N-type polymers. OX work when a conductive polymer is in contact with ions and solvent materials of an electrolyte, allowing it to regulate electron and ion transport simultaneously. OX have a high efficiency in ion to electron transduction and sensor signal amplification. OX have become increasingly popular in the healthcare sector due to its advancements as a high-efficient transducer for electrochemical biosensors. Song's review article titled Applications of Organic Electrochemical Transistors in Flexible Bioelectronics focuses on the most prominent bioelectronic applications of flexible OX. OX have simple structures which lead to the simplification of the manufacturing process. The employment of organic materials in the fabrication of OX leads to the possibility that they can be made on various substrates, for example, flexible types or even stretchable ones. This is a major advantage. Another major advantage of OX is its compatibility with many fabrication techniques, including photolithography and printing. Printing techniques are cost-effective, and their versatile fabrication methods provide numerous opportunities for large-area electronic component manufacturing. These typically have fewer steps and are compatible with unusual substrates. Inkjet printing is yet another popular method for producing OX. Because inkjet printing has a relatively high resolution and low requirement on substrate morphology, it has been used to fabricate OX. Flexible OX have been extensively studied for metabolites detection, and they show great promise for wearable health monitoring. Wearable metabolite sensors have high performance requirements, including its sensitivity, selectivity, and robustness. Using flexible OX, Song's group demonstrated a versatile metabolite sensing platform. OX were fabricated on a thin PET substrate and demonstrated good bending technique. Flexible OX have been used to sense enzymes such as uric acid, glucose, and cholesterol. Additionally, they have been implemented into DNA sensors and protein sensors, part of a push to increase point-of-care testing. Because of their high transductance, low working voltage, and biocompatibility, OX are also promising amplifying transducers for electrophysical monitoring. So to summarize, OX are inherently advantageous for flexible bioelectronics, as evidenced by many impressive advancements in recent decades. Now on to OFETs, the final application of organic flexible electronic devices in the biomedicine sector for today's presentation. Moreover, with the growth of the Internet of Everything, the IoE, there has been a push for connectivity beyond just electronic devices. There is a want for connectivity to everyday objects, thus there is a need for advanced sensor systems that will be able to accomplish this. Currently, the solution to this is through sensors connected to printed circuit boards, PCBs. However, it's not cost-effective and hard to achieve the flexibility required in some circumstances. Thus, there's an ongoing switch to using organic materials, as they're being studied as a feasible alternative due to its electrical, optoelectrical, and mechanical properties. As such, Huang, in his review article titled Printable Low-Power Organic Transistor Technology for Customizable Hybrid Integration towards the Internet of Everything, postulates that an organic FET-based flexible hybrid integration system can achieve this. Organic field effect transistors, or OFETs, are field effect transistors that use an organic semiconductor as their channel. They are also known as organic thin film transistors, and they are distinguished by their inherent flexibility, lightweight, low power consumption, ease of integration, high sensitivity, and large area manufacturing. These can also function as switches, amplifiers, transducers, drivers, and data storage components for many different applications. The proposed hybrid sensor systems combines silicon ASICs and OFET circuitry, which is illustrated here on the screen. There are many benefits to an OFET-based flexible hybrid integration system. Firstly, FHI is an emerging concept which seeks to combine the strengths of both flexible sensor technology and silicon integrated circuits. The silicon IC chips in such a system performs high performance and complex signal processing, while the OFET transducer provides flexible or conformable large area coverage and more friendly interfaces to integrate different sensing materials. OFETs can be manufactured at low temperatures on arbitrary surfaces over large areas using low-cost solution printing approaches by combining stacks of organic semiconductors and polymer dielectric material. Examples of this device technology for various sensors are also continuing to be researched, demonstrating its versatility in transducing various types of sense signals. Specifically, there has been extensive research in the applications of OFETs in bioelectronics due to their flexibility and impressive sensing abilities, just like with OLED, OPDs, and OX. Here's an image of that. OFET's core competitiveness in bioelectronics would be it being highly customizable for reducing the short design to product time, low cost manufacturing and ease of scaling up, and convenience for sensor material integration. This leads to increased levels of personalized health monitoring and point of care. These characteristics makes this device a promising technology of choice for flexible organic electronic devices, as the sensing capabilities can be printed on the flexible substrates in the biomedicine sector. This continues to be researched today. So to review, this presentation is on flexible electronic devices that are getting momentum around the world due to its increased research and future applications. Here's an image of its applications with screens and flexible bioelectronics. This was a review of what we covered today, and here are the works cited for all the information and the images I used. Thank you for listening to my presentation on organic flexible electronic devices in the biomedicine sector.